we're starting our unit on moles. Moles are very important in chemistry, but before we do that, we're going to look at dimensional analysis. So this is the process of solving stoichiometric and other types of problems by including and canceling units. So we're going to solve problems by canceling out the units. So the first thing we have to do is write down what we know. So 1 atmosphere equals 760 milligrams of mercury. So to set up the problem, we start with what we're given, 1.64 atmospheres, and we're going to multiply by this. So what we have, the atmosphere, that's going to go on the bottom, and 760 milligrams of mercury goes on top, and we get 1,246 millimeters of mercury. And with significant figures, that's 1,250. So the units that you want to cancel, what we have, they're going to go on the bottom. The units that we're trying to get to, what we want, go on top. Now we have miles in meters. So 1 mile equals 1.60934 kilometers, and 1 kilometer equals 1,000 meters. So we have 15.2 miles. So we're trying to get 2 meters. First, we have to go to kilometers. So the 1.60934 kilometers will go on top, and the mile will go on the bottom. Now the next step is to get to meters. So we have 1,000 meters in each kilometer. So now we're in meters because our kilometers and our miles cancel. And so we get, with significant figures, 24,500 meters. Example number 3. 1 atmosphere equals 760 millimeters of mercury. So we start with what we're given. That's millimeters mercury. We're going to multiply again. This time, since we have this unit, our 760 needs to be on the bottom, so it will cancel out, because it has to be on the opposite side to cancel. And we get 24.403 atmospheres. So look at example number 4. This time we're going from milliliters to quarts. So what we know is 1 gallon equals 3.78541 liters. 1 gallon also equals 4 quarts. And 1 liter equals 1,000 milliliters. So we have 972 milliliters. We always multiply. So our conversion that shows us milliliters is this one. We want to get rid of the milliliters, so they're going to go on the bottom. Now liters, we can use this one. So the liters need to cancel out, so they'll have to go on the bottom. And make sure you're always writing your units. And so finally we have our 1 gallon and 4 quarts. And so that's the unit that we were trying to get to. Our milliliters canceled, our liters cancel, and our gallons canceled. And so we end up with 1.03 quarts. Okay, example number 5, we're having to change our miles per hour to meters per second. So we have 1 mile equals 1.60934 kilometers. So we have 52 miles per hour. So hour is going to be on the bottom. So the first thing we need to do is get to meters. So we start out the same way. Convert there. And there's 1,000 meters in a kilometer. So now we have meters. Now we have to get the hours to seconds. Since the hours are on bottom this time, for it to cancel out, it has to be on the opposite side. So this time it has to go on top. What we have will go on top. So we have 1 hour, and there are 60 minutes in an hour. And in 1 minute, we have 60 seconds. So our miles cancel out, and our kilometers, our hours, and our minutes, and so we have meters per second. So when we solve this, we get 23 meters per second. Some moles. A mole is a chemical unit of measurement that we are going to use in equations in chemistry. A mole is equal to Avogadro's number, which is this 6.022140857 times 10 to the 23rd, and is the molar mass of the substance. So the molar mass means that the number that you see on the periodic table for the mass is the mass of 1 mole of that substance, or 6.022 atoms of that element. And a mole is based on the number of atoms of carbon-12 found in 12 grams of pure carbon-12. So this is what 6.022 times 10 to the 23rd looks like written out. So Avogadro's number, or a mole, is similar to a dozen in that it refers to a number. So a dozen means 12 of anything, and a mole means you have 6.022 times 10 to the 23rd of anything. The atomic masses, like I said on the periodic table, are the molar masses of the elements. So the molar mass of each element is different because 6.022 times 10 to the 23rd atoms of carbon wouldn't weigh the same as 6.022 times 10 to the 23rd atoms of nickel. Nickel is bigger, and so it weighs more. This is also true for compounds. A mole of water doesn't weigh the same thing as a mole of carbon dioxide. So, if you have 1 mole of sulfur, you have 6.022 times 10 to the 23rd atoms. You still have 32 grams of sulfur. So if you have 1 mole, no matter what you have 6.022 times 10 to the 23rd atoms, formula units, ions, or molecules. To find the molar mass of an atom, you're just going to use the mass that is given on the periodic table. Ions are going to have the same mass as a neutral atom because the loss and gain of electrons has very little effect on the mass. So if we had 1 mole of tungsten, we would have 6.022 times 10 to the 23rd atoms, and we would have a mass of 183.84 grams. If we had 1 mole of iodine ions, we would have the same number of particles, and our mass would be 1.2609904 grams, I negative. So if we have 6.022 times 10 to the 23rd atoms of carbon, that would give us 1 mole of carbon, and its molar mass is 12.011 grams. And this time we have grams of xenon. We have 6.022 times 10 to the 23rd atoms, and that is 1 mole. So to find the molar mass of a compound, we look on our periodic tables and we see that zinc is 65.38 grams per mole, and oxygen is 15.999 grams per mole. So we just add them together and we have 81.379 grams per mole of zinc oxide. So we'll do the same thing for CO2. So carbon is equal to 12.011 grams per mole. Oxygen, 15.999. But this time we have 2 oxygens. So we have to multiply that by 2. So when we add that up, we get 44.00 grams per mole. So lithium phosphate, we'll do the same thing. So lithium, its molar mass is 6.941, but we have 3 of them. phosphorus, we have 1, and it is 30.974. And oxygen, 15.999, and we have 4. And when we add all of those up, we get 115.793 grams per mole of lithium phosphate. So try the next one on your own, see what you get. So you should have 82.034. Grams per mole. We can also use moles to convert. So when you're converting between mass and moles, you're going to use dimensional analysis. Moles are used to measure in chemical reactions. So this allows you to control the reactions and create specific amounts of products. So we need to find the mass of 4.5 moles of aluminum. So again, we're going to write down what we know. 1 mole of aluminum is equal to 26.982 grams of aluminum. So we have 4.5 moles. We're going to multiply that by 26.982 grams over 1 mole aluminum, so that our moles of aluminum cancel out, and we get 121.419. So for 3 significant figures, we have 121 grams of aluminum. So now we need how many moles are in KMnO4. So first we need to know the molar mass. So when you figure that out, 1 mole is equal to 158.032 grams. So we are starting out with 6.456 grams, and we're wanting moles. So we get 0.04085 moles of KMnO4. So now we're looking for mass. So what is the mass of 3 moles of hydrobromic acid? So 1 mole of of hydrobromic acid is equal to 80.912 grams. So if we have 3 moles, we would put our grams on top, the moles on the bottom to cancel out, and we would get 242.736. So we would have 243 grams of hydrobromic acid. So try the next one on your own. 1 mole of NaHCO3 is equal to 84.006 grams. So we can also convert moles to particles using Avogadro's number. So that's the 6.022 times 10 to the 23. So our first one, how many atoms are in 4.5 moles of aluminum? So 1 mole of aluminum is equal to 6.022 times 10 to the 23rd atoms of aluminum. And we want our moles to cancel out, so they will go on the bottom. 6.022 is what's going to go on top. So we get 2.71 times 10 to the 24 atoms of aluminum. And that is our answer. So this time we have how many moles are in formula units. So again, 1 mole is equal to 6.022 times 10 to the 23rd formula units. So we have 3.022 times 10 to the 18. This time moles will be on top because that's what we're looking for. And 6.022 times 10 to the 23rd is what goes on bottom. This time we get 5.018 times 10 to the negative 6 moles of KMnO4. So example number 17, how many atoms of hydrogen are in 3 moles of hydrobromic acid? So 1 mole of HBr is equal to 6.022 times 10 to the 23rd atoms of hydrogen, because we have 1 hydrogen and 1 bromine. So we have 3.00 moles So our moles of HBr cancel out, and we get 1.8066 times 10 to the 24th, or 1.81 times 10 to the 24th atoms of hydrogen. The next one, we need to know how many atoms of oxygen are in 0.023 moles. So this time, 1 mole of NaHCO3 gives us 3 moles of oxygen. And 1 mole of oxygen has 6.022 times 10 to the 23rd atoms of oxygen. So this time we're going to have more than one step. So we have our 0.023 moles times 1 mole of NaHCO3 and 3 moles of oxygen. Then we have 1 mole of oxygen, and our atoms So our moles of oxygen cancel, and our moles of sodium bicarbonate cancel. We get 4.2 times 10 to the 22 atoms of O2, or of oxygen. So example number 19. If we had 0.4 grams of iron 3 nitrate, how many formula units would we have? So first we need to know how many grams are in 1 mole. So in 1 mole, we have 241.857 grams. So we start with what we were given, 0.400 grams. We want to get to moles, so we can get 2 formula units. So 1 mole is 241.857 grams. And in each mole, we have 6.022 times 10 to the 23rd formula units. So our moles will cancel out, our grams will cancel out, and we're left with formula units, and we get 9.96 times 10 to the 20th formula unit. Example 20. What is the mass of 7.258 times 10 to the 12th atoms of silver? So try to do this one on your own. So go ahead and pause the video. Okay, so the first thing you needed to know is that 1 mole of silver is equal to 107.868 grams of silver. So if we had 7.58 times 10 to the 12th atoms, we need to know how many moles we would have. And now we can go to grams. So you get 1.300 times 10 to the negative 9 grams of silver. Percent composition is the ratio of mass that each element in a compound contributes to the total. It is a way of breaking down the compound to show the percentage of each atom or ion by the mass. So it's commonly used to determine the percent by mass of individual elements within the compound. So look at the example. So what is the percent composition of each of the elements in sugar? So first we're going to look at carbon. So we're going to have, we'll figure up our whole, what 1 mole of sugar equals. So 1 mole of sugar is 342.297 grams. So now we need to know how many carbon, or what the mass is for just carbon. So whenever you add up 12 carbons, we get 144.132, and we're going to divide that by the whole, so what the entire compound is. And then multiply it by 100 to get percent. And we get 42.11%. So we'll do the same thing for hydrogen. In hydrogen, there are 22.176 grams of just hydrogen. And you get 6.48%. So we do the same thing with oxygen. we get 51.41%. So given the percent composition of both potassium and iodine, so again, we need to know what the molar mass of Ki is. So 1 mole of Ki is equal to 166.002 grams. So let's look at just potassium first. We have 39.098 is our mass for potassium. So we get 23.55%. Now look at iodine. We have 126.904 grams. We get 76.45%. So next we have what is the percentage of carbon in baking soda. So this time we just want carbon. So carbon is equal to 12.011 grams over 84.006 grams times 100. So we get 14.30% for carbon. So we can also use percent composition to determine the percentage of water within larger compounds like hydrates. So hydrates are compounds that have water. Instead of single elements, compare the mass of the dry compounds against the mass of water. So what is the percentage of water in copper sulfate pentahydrate? So the first thing we need to do is find the molar mass of this compound. So 1 mole that is 249.683 grams. So we're looking for the water. And so when we add up the value of 5 waters, or the mass of 5 waters, we have 90.075 grams over the whole compound, 249.683 times 100, and we get 36.08% water. So example 24, determine the mass, the percent by mass of the anhydrate in calcium chloride dihydrate. That should be dihydrate. So the anhydrate is the part without water. So we're looking for just this. So again, the first step is to find out the mass of the whole compound. So 1 mole equal to 147.014 grams H2O. And it would be a good idea to go ahead and pause the video and make sure that you're getting the same molecular weights or molar weights whenever you're trying to find the mass of these. So we're looking for just CaCl2. So the mass of that, 110.984 grams over 147.014 times 100. So you get 75.49%. Now we have empirical formulas. So empirical formulas represent the simplest ratio of different elements in a single compound. This is a simplified version of the molecular formula, and it can be used to predict the formula of an unknown compound in the lab. Historically, much of what we know about compounds was developed using empirical formulas. So to calculate the empirical formula from molecular formulas, you just divide the subscripts of each one, and the resulting numbers are the subscripts for the formula. So for this one, octane, we have an 8 and 18. So those are both divisible by 2. So we can make it C4H9. And so there's nothing else that there's no other number that's divisible but that we can use to divide both of those. So that would be our empirical formula. So for fructose, all of these can be divided by 5s. So CH2O is the empirical formula. And this one, they can each be divided by 2, so HCO2. And when you're looking at ionic compounds, they are already simplified, so they're already in their empirical formulas. So now, if we're looking for an empirical formula when we have a mass of each element, so we have a compound that has 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. What is the empirical formula? So for each type of element in the compound, we're going to convert to moles. So for calcium, we have 1 mole of calcium over 40.078 grams of calcium. Get 0.3368. We have 10.8 grams of oxygen. In 1 mole of oxygen, there are 15.999 grams. So with that one, we get 0.6750. Then we have 0.6750 5 grams of hydrogen, times it by 1 mole over mass of hydrogen. And we get 0.6696. And all of these are moles. So now we take the smallest number, so that would be calcium, and we're going to divide each one by that number. So we're going to divide this by 0.3368. So we get 1 here, 2.004, and 1.998. So these are very close to 2. So our chemical formula would be CaOH2. So now determine the empirical formula for a compound that is 75% carbon and 25% hydrogen. So since we have percentages, we're just going to pretend like we have a 100-gram sample. So we'll say 75 grams of carbon and 25 grams of hydrogen. So again, we're going to convert to moles. 1 mole of carbon over 12.011 grams. We get 6.244 times 1 mole of hydrogen over 1.008 grams. We get 24.801 moles. So we're going to divide by the smallest one. So that's this one, 6.244. So that gives us 1 there. And 4 here. So our compound would be CH4. Okay, example number 28. So what is the empirical formula of a compound which is 71.98% carbon, 6.71% hydrogen, and 21.3% oxygen? So again, we'll pretend like we have a 100-gram sample. So we'll make these into grams. And then we need to convert them all to moles. So 1 mole over 12.011 grams of carbon carbon, we get 5.99283. For hydrogen, we get 6.6567. And oxygen, 1.331. Okay, so oxygen is the smallest this time, so we're going to divide each one by the smallest number. And for carbon, we get 4.5. For hydrogen, we get 5. For oxygen, we get 1. Okay, so since we have a 5 here, we're going to multiply all 3 of these by 2. So that we have even whole numbers. We have to have whole numbers for our empirical formula. So what we get for our empirical formula: 9 carbons, 10 hydrogens, and 2 oxygens. So C9H10O2. A molecular formula is the chemical formula of a molecule that includes how many atoms of each element are present. So this is the actual formula. So to calculate these given an empirical formula and a molar mass, we calculate the empirical formula. So (7.19 grams of phosphorus and 92.81 grams of bromine. And we get 0.232 moles of phosphorus and 1.1615 moles of bromine. So we divide by the smallest one. And we get 1 and 5. So P, BR, five. So now that we have the empirical formula, we need to find the molecular formula. So we find our mass of our empirical formula. So we have bromine, which is equal to 79.904 times 5. So that has 399.52. And phosphorus, which is 30.974. So when we add those together, we get 431 grams. So in this case, the empirical formula is the molecular formula. Okay, our last example. Naphthalene is a compound containing carbon and hydrogen that is used to make mothballs. The empirical formula is C5H4. Its molar mass is 128.16 grams per mole. So what is the molecular formula? So we need to find out the formula, or the molar weight, for the empirical formula. So carbon, 12.011 times 5, and hydrogen, 1.008 times 4. So when we add those together, we get 64.087. So now we'll take this number and divide that by our molecular weight. So we have 128.16 divided by 64.087, and we get 2. So that 2 tells us that we are going to multiply the empirical formula by 2, and that will give us the molecular formula. So C10H8, and that would be the molecular formula for naphthalene.